Hello everyone, this is József Nagy here and welcome back to the Redux live stream where I revisit my videos from 7 years ago, starting with the CFD basic playlist, and currently we are on tutorial number 3 where we take a look at grid convergence. So if you're watching this video later as an already rendered video on YouTube, then just go into the comment section and then see when the actual tutorial starts, because now I'm going to wait for people to arrive. So if you're watching live, then is my audio okay? I hope it's still okay. Okay, hi Raj, how are you doing? I can see that people are arriving, very good. Let's wait a little bit. Audio is good. Hi, S.Wiesinger. Good to see you. Okay, so today the video that I'm going to revisit is going to be here in my CFD Basics series, this Understanding Grid Convergence Part 1, and I will concentrate on the first half and add some suggestions that I would do now in November 2021 in comparison to 7 years ago, and then in the next live stream we will then continue with Part 2. Okay, Raj is working on a turbine meshing. That's challenging. I can imagine that that's a lot of work. Okay, so as people are arriving, I will just maybe start with the video. I don't want to listen to it. I just want to go through it. That's part 2. That was the wrong tutorial. I want to go to part 1. Where is it? Here it is. Part 1. Is this the correct? Yes. Okay. So good. So this is what we want to take a look at. It's 1D simulation of a compressible flow of a pressure wave. In this case, a supersonic flow, and what we will take a look at is the velocity profile, the pressure profile, and the temperature profile in this compressible flow, and then how the pressure wave or the shock wave is being transferred with the simulation, and it should be a discontinuous jump, but you have always numeric diffusion, so it is smeared over a couple of cells. And I want to show you the influence of mesh refinement, but also a little bit refine the technique that I showed you here in this tutorial. Okay, so this is just the introduction. We will use set fields in this tutorial, so I will also talk a little bit about set fields, but in later live streams we will take a look at set fields in more detail. A little bit about blockMesh. In the previous live stream we talked about it in more detail, and we will run the simulation of this shock problem with the solver called SonicFOAM. Now, and at this point I want to mention that yes, in versions, in the OpenFOAM.org version, in versions 7, 8 and 9, SonicFOAM was discontinued. But I will show you how you can run this tutorial in versions 7, 8 and 9. In version 2012, 2106, SonicFOAM is still available, so in the .com versions you can just use SonicFOAM, and for the .org versions I'm going to show you how you can still run this and what the difference is going to be. Okay, so we are running a compressible transient simulation which can run laminar and turbulent flows. We are sticking with laminar flow, and it is a non-isothermal solver. Okay, yeah, so I'm not going to go into the solver here. Yeah, so Here I just copy the shock tube tutorial. Okay, so then let's just take a look at it. I have a gnuplot script that I set up, and afterwards in the description box, so once this live stream rendered as a video, in the description box below you will have a download links of this session3.zip, s3.zip file, just like I had already one for session 1 and 2, and you can download all the files from my GitHub account using that link in the description box below. Now for the live stream, just follow along, just watch what I'm doing, and then later on you can replicate it. Okay, so I have now the gnuplot script, and now I'm going to copy from OpenFOAM version. I'm just going to use version 2106. You can use 2012. Not a lot of things changed in this solver, so it doesn't matter. Compressible solver, sonic foam, and laminar. And then I'm going to just copy the shock tube tutorial here. And this is now so I just copied the out-of-the-box shock tube tutorial. Let me just take a look at what I want to call it. Yeah, shock tube, that's fine. Okay, so then let's just go into shock tube. So what do we have here? And I'm just going to open up this in Explorer. So we have the 0.org folder, so no 0 folder, constant, and system. So now if I open up the all-run script, we have this function restore 0 directory. This is nothing else than copy the 0.org folder and create the 0 folder. So this is just a backup folder, 0.org, and it creates an actual 0 folder. Then we run blockmesh, then we run setFields, and then we run sonic foam, and then we do some post-processing. Okay, so that's all it is. And so let's do it step by step. So first we run blockmesh. So let's take a look at the blockmesh dictionary here that we are dealing with. So we have 8 coordinates for our geometry. As you can see, it starts at -5 and it goes until +5. So our geometry is 10 meters long, and it's 2 meters high and 2 meters wide in the Y and the Z direction, but we are only using one cell in the Y and the Z direction, so we only use 1000 cells in the X direction. And this is what I'm going to do in the next live stream. Take a look at what happens if I reduce this to 100, and take a look at what happens if I increase it to 10,000. But let's just leave it with 1000. This is the default value. And then I have 2 values on the side. So in the -x and the plus x direction, I have a type patch, and everything else is empty. So with this, we tell the simulations that we don't want to solve the equations in the Y and in the Z directions. So nothing really fancy here. So if I just execute blockmesh, first I want to load my version 2106. Oh, SO1291, nice to see you. Also nice to see you. I hope you are doing well. Okay, so now I just execute blockmesh, and now I don't have an open.foam file here, so let me just open up the mesh and the geometry in Paraview, apply it, so just to have an idea what we are dealing with here. Okay, so we have the sides boundary. As I mentioned, it's in the -x and the +x directions, and we have the empty boundary here on the sides. And we have 1000 cells, so it's a lot of cells here. You can count from 1 to 1000 if you are bored, but believe me that these are 1000 cells, and we will solve these the equations only in the x direction. Okay, so this is our mesh. It's very simple. Then before I go to set fields, let's just take a look at the initial conditions. So now here we have P, the pressure, T, the temperature, and U, the velocity. So these are the input files for sonic foam. Let's take a look at them. For the velocity, we initialize the velocity with 0, 0, 0, and on the sides, or more or less outlets, we use the zero gradient boundary conditions. And on the empty boundaries, we use empty, of course. Then for the temperature, we also use zero gradient and a temperature of 1. So this is a very constructed case, so the temperature is very low. And the pressure is 0 at the beginning. And here it's also zero gradient at the boundary. So this is a very non-physical example, but this is a very well-known analytical example where you can calculate the pressure profile as a function for a certain time step analytically. So this is why it is in OpenFOAM. So the pressure is in Pascal, the temperature is in Kelvin, and the velocity is in meters per second. So for now, we assume a velocity of 0, a temperature of 1, and a pressure of 0. And we will take a look at then what we will do in set fields with that to initialize the initial conditions, but the boundary conditions are zero gradient at the ends and empty everywhere else. So this is not very fancy, but this is what it is. Okay, so here we have now in constant, we have thermophysical properties and turbulence properties. For turbulence properties, it's very simple, it's just laminar. And for the thermophysical properties, we have now a certain assumption for the gas. So for example, we are using a perfect gas with a molar weight of 28.9. So this is the or molar weight of our gas. Then we have a specific heat capacity of 1000. This is the enthalpy, so we set it to 0. Then the viscosity is 0, so this is an inviscid fluid, and it has a Prandtl number of 0.7. So this is more or less air. Of course, the viscosity of air is non-zero, but we assume it to be an inviscid fluid, and you can assume this because the velocity is very high, so the convection is more dominant than the diffusion in the Navier-Stokes equations. Okay, so this is it. And then in system, you have a couple of files here. Okay, so blockMesh we already took a look at. Then in controlDict, we will run the simulations for 7 milliseconds with a time step size of 10 to the power of minus 5, and we will write out in millisecond intervals. So it is a very fast process, and we will then save 7 time steps. We have cool functions that I can just advise you to use if you are fed up with in Paraview, if you want to use the calculator and you want to multiply the magnitude of the velocity with something to calculate something else, and you have to always do the square root of velocity x times velocity x plus velocity y times velocity y and plus velocity z times velocity z. You can just calculate here the magnitude of the velocity, and then you don't have to worry about the components for the calculator in Paraview. So with this function, you can calculate the magnitude of the velocity, and this will output it for you as a scalar field. So this is very handy function in certain cases. Of course, Paraview automatically calculates the magnitude, so it visualizes it, but it's still a pain if you want to use the calculator and use the velocity in the calculator. We will do that because we want to plot the magnitude of the velocity later on in post-processing. So this is why we calculate it. In FV schemes, you can see that we use the upwind discretization, which is perfect for us because we want to see the effects of numeric diffusions, and as in the future and in follow-up live streams, we will see upwind is introducing the highest level of numerical diffusion. Okay, so FV solutions, we just use the standard tutorial values, and also in Pimple we use two autocorrectors, one n corrector and 0 n orthogonal correctors. And in this file is the setting which we have to change for the openfoam.org version in order for this simulation to run with versions 7, 8 and 9. Okay, then in setFields, what are we doing in setFields? So now we modify the initial values from these unphysical values of 0 and 1 Kelvin to a more physical value. Okay, something just happened. Let me just see. I'm okay. Whatever happened. Lucas Costa just subscribed. Thank you for the subscription. Okay, I just saw it. Thank you for the subscription. Okay, so now the default field values. So this is what we will now set in our initial conditions. So we will initialize our internal field with some default values, and we will rewrite these files. And this is why we have this backup folder. If we screw something up, then we can just delete the 0 folder and we can just redo setFields with our backup files. Okay, so what do we do? So for the velocity, we still take the same velocity values, but for the temperature, we use a more physical value of 348.432 Kelvin and a pressure of 1 bar. And then we use a box to select cells, and then this box is going from 0, so from the center. Let's just take a look at, okay, so if I just take a look at our geometry like this. So this box starts from the center, so half of the cells and everything to the right, because it goes up until +5. So imagine a box from 0 to 5, and then going from -1 till +1 and -1 till +1. So the box is covering 500 cells on the right hand side, and in those cells we assume a lower temperature of 278 and a pressure of 0.1 bar. And we will just run these stock values. We could adjust these to different values. Be my guest to use, for example, here 1 bar and here 10 bar instead, and then see what happens. But I'm just going to use here the default values because it still does the same. It has the same effect. Okay, so on the right hand side we will artificially lower the temperature and the pressure, and then this pressure difference will create a shock wave traveling through our domain, and then increase the velocity, and then also change the temperature profile. Good, so this is the idea, to have a pressure difference and then have a pressure wave, a shock wave going through our 1D geometry. And then in the end we will run the simulations, and then we will extract some data, and we will use the sampling function, and we want to extract t, the magnitude of u, which we calculated with this function, and then and the pressure, of course, or we want to select a line in the center of our domain going from almost 5 until, or almost -5 until almost 5, and we will use 1000 points and select the values along those 1000 points, so in each cell, and it's in the center of the domain, so it's really on the y and x-axis of 0, just going from the start till the end, and we will only consider the x coordinates. So we could just use here, you can just type here in blah and then see what is the error message, what are the options here for the axis, but we will only now output the x coordinates because we are only dealing with an x one-dimensional case in x direction. Okay, so this is what we will do. So I will just now run setFields. Here you go, and now we will take a look at what happened here. So I will just refresh here. I hope that this will load in. Yes, so the velocity is 0, so nothing changed here. Then the temperature is now, we have a high temperature value on the left hand side and the low temperature value on the right hand side, and the same for the pressure. So we have a low pressure value on the right hand side and the high pressure value on the left hand side. Okay, and now I can just execute SonicFOAM. Okay, and now the simulation runs, and it takes a while. Okay, so until SO1291, probably using VS Code or Sublime Text is a better option to navigate OpenFOAM cases using their integrated file explorer. Yeah, possibly. I prefer Notepad++, but of course you can use VS Code. It is a nice software. Good, so the simulation finished, so now I can refresh, and it doesn't refresh for some reason, so I'm just going to open it up again. Now I have the 7 time steps, and now we can take a look at, for example, the pressure in Paraview. And as you can see now, here this pressure wave is going through our domain, and then here the pressure is expanding. And this is what it should look like. The temperature, here, another interesting point here is that our pressure wave compresses the temperature, the gas, increasing the temperature. And here the temperature is further reduced. So here we have a very cold region and here a very hot region. Okay, so. And in the next live stream, we will take a look at what happens if you calculate this with 100 and 10,000 cells. But for now, what I want to show you, because this is also what I'm showing you here, is how can you evaluate this as a diagram. Okay, so here I'm doing 100 cells, so this is something for the next live stream. So yeah, so let me just, okay, this is 100 cells with I already showed you the files, I already showed you the mesh, so I already executed set fields here. Yeah, okay, set fields still here. Now I run the simulations, and here we go. This is what I just showed you with 1000 cells. Yeah, so this is now 1000 cells. Very good. Yeah, and then, okay, and this is something for the next next live stream regarding the Courant number. But what I wanted to show you is in 7 years ago I used this plot over line to show you the diagrams in Paraview, and then I loaded the results in LibreOffice. But now this is why I have here this gnuplot script, because now I want to show you the possibilities with gnuplot and how you can really utilize the post-processing script. And for that we have to still run the post-processing step. So it's not just possible to run runtime post-processing during the simulation with certain functions, but you can also do it afterwards with the post-process function. And what this does, this runs the sample function, and it doesn't run it for the 0 folder. Okay, so this now runs this function for all the saved time steps, and now we have a post-processing folder with sample and the individual time steps and 0.07. So here we have one XY file which then includes now the X coordinate, then the temperature, then the velocity, and then the pressure. And we can now plot this. And I just open up the gnuplot scripts. That's just to show you what I prepared here. So I have my lines set up. Then the first velocity PNG is from -5 to +5, and then the velocity is from 0 to 300 meters per second. And then I load the shock tube post-processing sample at the last time step, this XY file, and then the first column and the third column, which was the velocity, and this is wrong. This really should be 1000 cells. Then I have create a second PNG with the same file, just the second column where the temperature was located at, and it's also 1000 cells, and then the pressure. Okay, so the temperature is between 200 and 450, and here it is between, the pressure is between 0 bar and 1 bar. And then the first and the fourth column, and then 1000 cells. And now if I execute this gnuplot script, now I generate 3 really nice figures with version 21.06. So this is what the velocity looks like. So the shock waves is almost at 4 meters, so this should be a discontinuous jump, then a constant value, and then it decreases down. Then the temperature, it also, again, here you have a high pressure region, or no, high temperature region, then a low temperature region, and then it goes back to the original value. The same is true for the pressure. So here you could now add, I don't know, we could add, let's just add the, another time step. So 2, not 10, but this, and then maybe not 0.07, but 0.03. And let me just, no, this is the right syntax, sorry. So let me just add this here and this here. So this is then the third column and then the fourth column. Let's see what's happening here. Gnuplot, and now you can see that the velocity, so it propagates to the right hand side. So this continuous jump is moving to the right, and then this this expansion of the gas is also expanding to the left hand side. But this point is always at 0, it stays at 0, and then only the decrease, so the slope is getting smaller and smaller. And also this is then the difference between time 3 milliseconds and 7 milliseconds. You can plot all 7 time steps, and this is then the pressure at 3 milliseconds and 7 milliseconds. But this is not what I want to show you. Actually, what I want to show you is the difference between 21.06 and version, I believe 8 is what I have installed. So for that, I will run this case a second time. And then see the differences between the .com version and the .org version, because the Sonic Foam was discontinued for versions 6, 7, 8, and 9. So let's run this same case with the .org version. Okay, so as you could see, I'm running her version 21.06, and I will just load version 8. And I will just copy now the tutorial from version 8, and tutorials, compressible, and it's not Sonic Foam, but raw pimple foam. laminar, and shock tube. And I will just call it shock tube 2. And in shock tube 2, it is almost the same. You can go through the text files. The only difference is in FV solutions, as I mentioned. And here in the pimple directory, you have this optional entry transonic yes. And with this, you solve more or less the same equations as in SonicFOAM. So you can run this tutorial also with the .org version, but you have to use a raw PimpleFOAM instead of SonicFOAM, and you have to use this optional entry transonic yes in order to get the same results. And so for that, we just run blockmesh, and now we are using version 8, and the same is then in version 9. And with version 7, set fields. Okay. Oh, thank you very much for your donation. This is very kind of you. My first donation, so thank you very much. Directly without creating your own script. Thank you very much for your input. And also again, thank you very much for your donation. Very generous. Okay, so coming back to version 8, set fields, and now we have to run raw PimpleFOAM. Now this runs the same simulation. Now this ran and cannot find required object. Okay, no, magnitude U is still there, so I don't know, I don't understand this warning here. But oh well. So now we have to run the same post-process function. So there is no zero option in this version of OpenFOAM. Okay, so now we have our post-processing function, post-processing folder with that function. So now in ShockTube 2, we should have the same results. Let's see what happens if I just execute gnuplot. Okay, let's just get rid of this. And now, as you can see, both the .com version and the .org version calculate the same velocity profile, also the same temperature profile and the same pressure profile. So with this, now you are able to run your simulations in both OpenFOAM.org and the OpenFOAM.com version. Yeah, so this is what I wanted to show you, but since it is very early, possibly I could even run the simulations with 100 and 1000. And then I can go in the next live stream, go on to the next tutorial. So that would be really good. So let's just do that. ShockTube 3 is then the 100 case, and then ShockTube 4 is then going to be the 10,000 case. So here I reduce it to 100. Okay, so I just copy the 0 folder, blockmesh, set fields, and then SonicFOAM. Okay, so with the 100 we have the results, and now let's just run this post-processing function here. Okay, and in ShockTube 4, let's just increase the number of cells to 10,000. blockmesh, then set fields. And now let's just see what happens if I run SonicFoam. It crashed. And okay, this was the one thing that I wanted to postpone to the next next live stream, but we can talk about that. And you most probably know about the Kuro number. The Kuro number is a dimensionless number, a numeric one, which then reduces or controls the time step size. So the Kuro number is defined as the velocity time delta t divided by delta x. And usually this value should not exceed 1. In some cases you can, but usually this should be less than 1. So if we assume that the c value is 1 and then we reformulate this equation to be so delta t equals c multiplied by delta x divided by u, then we have a condition for our time step size. And here the maximum Kuro number is above 1. So what I have to do now is reduce my time step size. So with this, the simulation will take longer, but nonetheless, this is going to be a more stable simulation. Okay, so hi Woze. Hello Josef, I have been through the 3 weeks OpenFOAM course and your videos are absolutely great. So I'm happy about that. I'm glad to help. Just wanted to take the opportunity to thank you for the fantastic educational content. You're very welcome, and I hope you also enjoy the tutorials of others, because there are also high quality content on wiki.openfoam.com from others. But I'm really glad that I could help you. Okay, so this simulation is running. So let's just set up the gnuplot script for that. So let's just say this is 1000cell.com. 1000cell.org. So let me just write this down here. Okay, just so we can see the difference. And then we add 2 more lines. And this is 3 and 4. And this is then 100 cells and 10,000 cells. And then ShockTube 3 and 4. Good. So let's just copy paste these here. And of course now I have to change this to column 2 and column 4, not 5, 4. Okay, let's see. Okay, this is still running. We are at 2 milliseconds. So yeah, so this is now a thing. So this is something that you cannot avoid. If you reduce the mesh, then you also have to reduce the time step size. This is the Courant condition. The CFL number, usually in English-speaking publications, they talk about the CFL number because it's Courant, Friedrich, and Levy who came up with it. In German-speaking regions, you talk about the Courant number. But it's the same thing. Okay. Then let's just see what we have here. Okay, so then we can, so this is something I talked about. Maybe let's see whether I forgot something here to mention. But really, okay, so I could also load the values in Paraview. This I did forget. So 1000, then let's go to 100. We don't have an open.foam file here. And then let's just paste it also here. Oh, it's slow. Okay, so this is the 100 case. 100, and then let's load the 10,000 case as well. 10,000, and then now I want to actually place some y normal planes in there for a very simple reason. Because I want to shift them. So I want to shift this by maybe in the z direction by -2, and then this also by -4. So now we have here the pressure, then the pressure, and then the pressure, and possibly at an earlier time step at 4. Very good. So now we can really see the difference in the quality of the resolution. So here with 100 cells, we have the increase in pressure over 2 cells, but because the mesh is so coarse, it ranges over a larger area, whereas this discontinuity is sharper because the cells are smaller, and with 10,000 cells you cannot really see any pressure to the eye. So with 10,000 cells you are very exact. So here also in the temperature you can see that this is a very, very sharp jump, but if you really zoom in, then you can see that there is a numeric diffusion here, but since the mesh is so fine, you can remedy the numeric diffusion with the cell refinement. So this is the one possibility, and in a future live streams we will take a look at how you could reduce it with some numeric settings. Okay, so let's take a look. Okay, so the simulation finished, so I can just refresh this and then jump to the last time step. It's the same, so we have a very nice jump in the temperature, pressure, velocity with the finest mesh, a good discontinuity with 1000, and the horrible discontinuity with 100 cells. So this should show you what the grid refinement does and why it is so important to run a grid dependent study in each project at least once to understand the behavior of your numerics on different grids and what is a reasonable. Because usually people just run, just assume that their grid refinement is good enough, but it is a very good idea to have an idea about grid dependence as well. Okay, so now all I have to do is run the post-processing function, and I believe I did not run this here. Did I run it here? Yes, I did. Okay, so now we have the post-processing functions, so I can just execute the gnuplot script, and then let's here let's just open up the velocity, and now this is what the results look like. Oh, sorry, I called it .org. I don't want to piss off anyone, so I ran here the .com version. Of course, that's just a copy-paste thing, but please go ahead and run the 110,000 case also with the .org version, and you will see that the results are equivalent. Okay, so you can see that .com and .org calculates the same values. It's just the solver is called differently, and you have to use one additional input in FV solutions, but the results are equivalent. And here now you can see the difference between 100 cells, 1000 cells, and 10,000 cells. Okay, so this is now velocity, then the temperature, and you can see how bad the temperature is. It is even unstable for 100 cells, so it is very bad. What happened here? So I think I made here a mistake for the temperature. Yes, I forgot. This is 2 and this should be 4. I don't know what happened there. Okay, so let's close this and rerun the script. So that was a mistake from my side. Okay, now here you can see the temperature is very bad with 100 cells. With 1000 cells it's better, but still here you have problems. And then for the pressure it is very, very nice, and we could compare this with an analytical solution, but it's more or less the blue curve here. You can run this also with 100,000 cells and see the difference between 10,000 and 100,000 cells. Of course, in 3D, you cannot just increase the number of cells by a factor of 10. Usually you do it with a factor of 2 or maybe even lower, but it is always a very good idea to run such a grid-dependent study in each project if you can allow it from a project time point of view. Okay, so that was really it. So the only thing the things that I wanted to change up here in this tutorial is using a gnuplot script, and so you don't have to import it in LibreOffice or Excel. You can immediately visualize your results. You could even now visualize each individual time steps and then compare those between .com and .org. It will be the same. So you can play around. You can also change the pressure values here and then see what happens if you have 0.1 bar and 10 bar, for example, or 1 bar on the low end and 1000 bar on the high end. So you can just play around with it and then take a look at it. But here, and also I wanted to show you, because this is a lot. I always get comments on this tutorial from users of the .org version that SonicFOAM is not working. You can run it with raw PimpleFOAM. So this is something that I wanted to show you, how to run this tutorial in the .org version. So this is what I wanted to talk about today. Again, SO1291, thank you for your donation. It is very generous. So thank you, thank you, thank you. So this is what I wanted to talk to you today. I hope that you liked this tutorial and that you learned something on top of the tutorial from 7 years ago. So with that, I would like to thank you for watching and listening. I hope that we see each other in the next live stream. Up until then, I wish you all the best and I hope to see you next time. Bye.